Welcome to this explainer. Today, we're tracing an absolutely incredible century-long journey, uncovering exactly how humanity decoded the explosive mechanics of the cosmos. We're going to see how our understanding of the universe's biggest explosions evolved from scattered, accidental sightings into a highly precise, multi-wavelength science. Imagine looking up, seeing something completely unprecedented in the night sky, and just brushing it off as a trick of the light. That is exactly how our story starts. Picture this. It's August 1885. French astronomer Ludovic Gully is hosting a public stargazing event, and he inadvertently spots a new stellar object. But he just dismisses it as scattered moonlight. He literally left it completely unreported. It actually took independent sightings by an amateur Irish astronomer, Isaac Ward, a couple of days later, and eventually a telegram from Ernst Hartwig later that month for the world to finally take notice of S Andromeda. This was a massive watershed moment, the very first extragalactic supernova ever observed by humanity. So, let's dive right into Section 1, First Glimpse Beyond Our Galaxy. It's crazy to look back at these missed opportunities. The sheer accidental nature of early astronomy meant monumental discoveries were nearly lost to history simply because observers didn't report them. Just look at how this played out. Gully misses his chance on August 17th. Ward spots it on the 19th, but he stays quiet. Hartwig finally sees it on the 20th, but gets this. He waits a full 11 days until August 31st to actually send a telegram. Honestly, it's a miracle the scientific community was able to catalog it at all. And to put this into perspective, you have to understand just how faint this object was to us on Earth. It reached a peak apparent magnitude of +6. Now, +6 means it was right at the absolute limit of human vision. It was just barely visible to the naked eye and only under absolutely ideal pitch-black viewing conditions. Catching this faint pinprick of light without the aid of modern instruments was just a tremendous stroke of luck. But here is the really fascinating irony of the whole thing. SN 1885A appeared in the Andromeda Galaxy, right? Well, in 1885, astronomers thought Andromeda was just a nearby nebula inside our own Milky Way. They had no idea they were witnessing a stellar explosion millions of light years away. So we managed to observe our very first extragalactic supernova decades before Edwin Hubble's work in the 1920s actually proved other galaxies existed. And to this day, SN 1885A remains the only supernova astronomers have ever observed in the Andromeda Galaxy. Moving on to Section 2, Defining the Supernova in the Early 20th Century. It wasn't until 1934 that the word supernova even entered our vocabulary. American astronomer Walter Baade and Swiss-American astronomer Fritz Zwicky coined the term. They needed to define this extraordinarily luminous stellar explosion, representing a vast energy release distinct from less energetic nova events. The scientific understanding was growing, and they needed to provide crucial clarity, officially separating these massive explosions from everyday stellar flare-ups. By making this strict distinction between an ordinary, less energetic nova and an extraordinarily luminous supernova with vast energy differences, Zwicky was able to do something entirely new. He initiated systematic searches using the 18-inch Schmidt telescope at Palomar Observatory. This targeted approach was an absolute game-changer, dramatically accelerating the rate of new discoveries far beyond the Milky Way. But here's the coolest part. They didn't just name these events. They boldly predicted the mechanics behind them years before telescopes could actually confirm it. The Baade-Zwicky hypothesis was a brilliant step-by-step chain reaction. Step 1. An ordinary massive star reaches its end. Step 2. Significant stellar mass converts entirely into radiation, which explains that blinding luminosity. And Step 3. The core transitions into an incredibly dense neutron star. Okay, that brings us to Section 3, the classification era. As spectroscopic technologies evolved into the 1940s and beyond, astronomers could finally analyze the chemical fingerprints of these distant explosions. Initially, Rudolf Minkowski's classifications were super simple. If an explosion lacked hydrogen lines, it was type 1. If it showed hydrogen lines, it was type 2. But by the 1980s, this evolved into a beautifully precise system. We realized type Ia explosions were actually thermonuclear events involving white dwarfs, identified by silicon absorption lines. Meanwhile, types Ib, Ic, and Io were all recognized as massive stars experiencing core collapse. It's like a giant cosmic puzzle falling into place. And those mid-century milestones came fast. We saw larger telescopes and electronic detection emerge. We had Jocelyn Bell Burnell's incredible pulsar discovery in 1967. Then in 1968, the Vela pulsar was found inside a supernova remnant. That was the smoking gun that finally proved the Baade Zwicky hypothesis, firmly linking supernovae to the creation of rapidly rotating neutron stars. Plus, as our catalogs grew, astronomers realized these massive explosions could serve as cosmic standard candles, objects of known brightness that let us calculate vast distances across the universe. Which perfectly sets up Section 4, Modern Supernova Astronomy. The year is 1987, specifically February 1987. An event designated SN 1987A appeared in the Large Magellanic Cloud, a satellite galaxy of our Milky Way. It instantly became the closest observed supernova to Earth since Kepler's star way back in 1604. Because it was so close, it offered us absolutely unprecedented observational detail. And this is where it gets wild. Theoretical models had predicted that invisible neutrinos carry away the bulk of the energy during a stellar core collapse, while SN 1987A proved it perfectly. Deep underground neutrino detectors right here on Earth registered an invisible burst of these particles from the supernova several hours before its visible light even reached our planet. We were literally feeling the invisible physics of a dying star before we could even see it shine. How cool is that? Looking at this century of progress, it's just breathtaking. We went from that accidental naked eye observation of S Andromedae in 1885, to Baade and Zwicky defining the supernova in 1934, to the Vela pulsar proving the neutron-star link in 1968, and finally SN 1987A launching neutrino astronomy in 1987. We evolved from gazing at a single misunderstood point of light to actively tracking invisible subatomic particles from collapsing star cores. So, from scattered moonlight in 1885 to neutrino bursts in 1987, what will the next century of cosmic monitoring reveal about the explosive universe around us? I hope this explainer has sparked your curiosity about the violent, beautiful mechanics of the cosmos. It really makes you wonder what breathtaking discoveries are waiting just out of sight tonight, right? Keep your eyes on the stars,